So good evening. Just take track of time. Cool. Okay. So I'll start with a few words about myself. My background originally is math, computer science, and physics. I then worked as a software engineer for quite a few years, and I also at some point took a break and did a PhD in the Weizmann Institute in systems biology, which essentially means that I've been doing mathematical modeling of all kinds of biological systems, not related to this talk. It was about bacterial metabolism. Yeah. Can you hear me like this, or do I need to use the microphone? It's better to use the mic. Okay, so I'll use the mic. No, I think this is okay. It picks me up well, I think. So it has nothing to do with this talk, just part of the background. And I'd like to start with a pop quiz. So my question for you is, starting 1950, by how much do you think the world population increased? Option number 1, it doubled. Option number 2, it tripled. And option number 3, it increased by 30%. Who thinks number 1? Doubled? A few. Who thinks number 2, it tripled? Majority. And who thinks number 3, it increased by 30%? Also a few. So the world population in 1950 was 2.5 billion people. Today it's 7.7, so it more than tripled in the last 70 years, which is quite amazing when you think about it. Like, it was not long ago, and there were only like more or less the amount of people that are today in India, China, and a little bit more. So this is about world population. Another pop quiz question: by how much did crop yield increase since 1950? And I would like to explain the question. So when I talk about crop yield, I mean that if I have 1 square kilometer of, let's say, a field of wheat, how much grains am I able to extract from that 1 square kilometer? So option number 1, 10 to 50%. Option number 2, 50 to 100%. And option number 3, 100 to 200%. How many of you think it's option number 1? How many of you think it's option number 2? And how many of you think it's option number 3? Okay, so we have the majority. It's quite balanced, but the majority went for option 1. And here also, it turns out that the real answer is option number 3. So the yield in fields has increased by 100 to 200%. It's an amazing number, at least in my opinion. And it was driven largely by what we call the Green Revolution that took place mostly in the 50s and 60s of the previous century. And there were 4 key drivers for this revolution. So the first one was the introduction of engineered high-yielding crops, especially for what we call broad-acre crops, which are wheat, corn, soybean, and rice. This is what feeds most of the world population. Of course, it wasn't using modern genetic engineering, but it was using hybridization, selecting high-yielding varieties, and also doing all kinds of spontaneous mutation inducing by all kinds of means. So this is one driver. The second driver was the introduction of controlled water supply. So most of the world used only precipitation-based water, and the introduction of smart irrigation systems, spraying, dripping, etc., and just having a man-made irrigation also increased yield significantly. The third one is the introduction of chemical fertilizers, pesticides, and herbicides. So if some of you are wondering where did the Dead Sea go to, this is where it went to. All the phosphates, all this chemical industry we love to hate so much, it did have some benefits. I'm not saying it was worthwhile, but it did have some benefits. This is what drives yield and what allows us to feed the world today. And the fourth factor is mechanization, all the introduction of mechanized plowing, seeding, harvesting, etc. also dramatically increased the yield we can extract from fields. And question number 3, how much of all of the crops that we grow are being wasted or lost after they've been grown? Option number 1, less than 20%. Who thinks that? Let's make it shorter this time. No one. Option number 2, 20 to 30%. A few hands. Option number 3, 30 to 50%. Most of you, if you read the intro to my talk, then you know the answer is 40%, more or less. It's depending on how you count exactly. So according to the Food and Agriculture Organization of the UN, about a third of the harvested crop is lost or wasted. And out of this loss or waste of food, about half of which occurs after harvest, but prior to reaching, let's call it the last mile, prior to reaching the retailer or the consumer. So really, a lot of food that we grow is just thrown or wasted away because of all kinds of inefficiencies, which brings us to the topic of my talk, and that's about Trellis.ag and our mission. So our mission is to reduce food loss and waste by optimizing the food supply chain management. So first, I'd like to tell you a little bit about the food supply chain, what it means, why it's problematic to manage, where does some of the food loss come from. So essentially, when we talk about food production or the industrialized world, we have industrialized facilities. Those are factories. Those have to do with logistics, trucks, mechanization, all of these kind of systems, man-made systems. And those systems, in order to act efficiently, first of all, they have limited processing capacities. They have strict quality requirements. For example, if Barilla wants to produce pasta, the grains, the durum grains, must meet a certain amount of protein inside them. If there's not enough protein in the grains, it can be thrown away. It cannot be used for pasta. And if it's not managed properly, it will be wasted. And that's true for many crops in many production systems. And of course, it requires strict planning. You need to know when to have the personnel ready, how to organize, when to clean, when to shut it down, when to operate it, every such facility. And they operate best when they can meet just-in-time requirements. On the other hand, or the problem lies in their supply, which comes from fields. And fields are highly volatile in many ways. They experience varying weather conditions in different years, different regions that may affect yield significantly. They are exposed to all kinds of environmental impacts like disease, again, pests, fires, all kinds of problems in irrigation, etc. All of that really affects the yield you can get from a given field. And they're also very sensitive to maltreatment, which means that if, for example, I have changed the personnel in a farm, or I haven't applied the right amount of, again, pesticides or stuff like that, chemicals change, water change, all kinds of different factors will severely impact the yield I will get. And all of that causes the system requires the system to operate with a relatively large buffer in order to be able to operate efficiently given the variability or the volatility of the input to food producing facilities. And in turn, that also induces waste when either production supply does not meet demand or if it exceeds demand. So this is where AI and ML, machine learning, come into play. And essentially, there are two ways by which these technologies and algorithms can be used in order to increase the efficiency of food supply chains. The first one has to do with predictions. So if we're able to construct models that are able to give us good yield predictions ahead of time, we can plan accordingly. If we can build machine learning models that can generate predictions that can forecast better the maturation time, when a field is going to be ripe, if I'm delaying now the harvest of the field, by how much will that affect quality, etc. Again, this is a leverage which we can use in order to optimize the supply. Another thing is if we're able to predict quality metrics. For example, we heard from a company that deals with milking stations, with dairy products, that even though they have some statistics on the amount of fat that in cow's milk and how that is dependent on the feeding mixture that the cows are fed, the dairy producers, you can only measure that in a facility, and often milk is routed to the wrong facility or is being routed to the wrong production line where it doesn't meet the necessary fat content, and therefore it has to be rerouted. Sometimes it's spilled. You can cry about spilled milk, but really there's a lot you can do if you can predict the amount of fat, for example, in order to operate your business efficiently and avoid waste. And this leads us to the second thing which we can do, and that's do smart planning, do optimization. Once we have the basic cornerstone of having predictions about what's going on and knowing what the limitations are, what are the rules of the game, we can now generate smarter planning and really integrate the planning with the output from the fields. It can be through optimized logistics according to predicted yields. It can be by using efficient and timely harvesting of fields, not pre-harvesting or post-harvesting that will affect the quality of the crop, and also going really into details of planning production according to the specific crop characteristics. For example, which I'll get to this example later, but just to tell you, give you an understanding of what I'm talking about. Let's say I'm producing potato chips, and let's say I have small potatoes. If I have small potatoes and I cut them into chips and I pack them in large bags, they will be at the bottom. And even though the potato chip bag will meet the weight label that is on it, the customers will return the bag. They will say, "You sold me an empty bag." Okay. However, if I'm now using the small potatoes in order to pack them in small bags, the effect will not be as significant. On the other end, if I have big potatoes, which I'll try and compress into small bags, they will break inside. They will not fit well, and I will have the opposite effect. So knowing the potato size in advance before I decide what I'm going to produce can help me reduce food waste. And production lines specifically for potato chips are calibrated according to strict size measurements. And as we'll see later, potatoes are wasted in this way. For example, and this is just one anecdote about where this comes into play. So now I'll go over three use cases or three samples of what we do. And I'll start with yield prediction. So a little bit about yield. So if I take a given plot, it doesn't really matter what crop. For most crops, it will show something like 30% variability in yield year to year. You can, for yourself, you can think if you consider this a large or small amount. To me, it sounds pretty large. Like having 130 tons per dunam or 70 tons per dunam sounds like a pretty big difference to me. And the variability is driven both by regional factors, let's say like weather, which all the fields in the region experience in the same way, and also by local factors, let's say a disease or again problems in irrigation systems, problems in how the field exactly has been operated and stuff like that. And when we as a company ask ourselves, okay, what signals we want to use in order to generate yield predictions, what is the raw material we're going to use? So we need to consider the trade-off between using regional signals, let's say like weather, which are easy to obtain, but are quite complicated to analyze, and field-level inputs like field-level samples or aerial satellite imagery or other signals which you can get at the field level and that can help us predict the exact either conditions or effects that this field experiences throughout the growth season. And of course, obtaining field-level data is harder than obtaining regional data. For that, you may need smart sensors. I'm sure there are representatives in the crowd from companies that do precision ag and similar stuff. So this is what is required in order to get field-level high accuracy data. And here I have a question. And the question for us, which we ask ourselves as a company, can we decouple the regional versus the field-level variability? So we had to take our decision whether we're going to take regional or high accuracy field level data. And we wanted to ask, okay, given the variability that we see in yields, can we decouple the effect? Can we say, okay, we can estimate that about 10, 20%, 30% out of the 30% variability year to year is caused by regional factors, and what amount of the variability is caused by field-specific factors. So we have time, I see I'm ahead of time. Let's take a minute to think about it, and you're welcome to propose ideas. And I will focus my question. Assume I give you a table, and in this table you have 10 years of history, let's say 2010 or 2009 until 2019. For every year, I tell you, for 100 fields, I tell you what was the yield in every field, okay? And I ask you, you have this table, years and blocks. You have overall 1,000 lines, 10 years times 100 blocks, and the yields. If you have some idea, how can you tell me, listen, this and that, and they're all from the same region, this amount of variability is due to regional effects, and this amount of variability is due to field level effects. So let's see if you have any idea. Or maybe did I explain myself well? Who understood the question? Okay, so about a half. So that's good enough for a start. Let's take a minute and think about it. And if someone has a suggestion, yes.
Preliminary.
Yeah.
You check if there's a correlation between the varieties, variables in the weather.
Mm-hmm.
You can select information about the weather.
Mm-hmm.
You see if the weather changes
Okay, so I will make life simpler. All of these fields are located in the same region. They experience the same weather. Okay, we're looking at weather. So I know that the weather that all the fields experience throughout these 10 years is the same kind of weather. It's the same kind. It's the same kind of crop and the same variety. Let's say we're talking about wine, so these are all Chardonnay wine. We'll see that in a second from Napa and Sonoma valleys in California. We know terroir is important, but let's see. So now we can ask ourselves, okay, we know, but we know. Let's make it data driven. Yes. Any ideas? Yes. Okay. And can you elucidate that and give me a simple way to do it? Yes.
So, for each field, you have the historical data.
Mm-hmm.
You understand for each field, it's regression.
Mm-hmm.
Either whether it's going, slope is on the rise or on the low.
Okay.
You can section it based off of year,
Mm-hmm.
year over year.
Mm-hmm.
You can look at, wow, 90 of the fields have a positive slope.
Mm-hmm.
10 of the fields have a negative slope, and you can see the difference, the variable difference between them. The year over year, the slope of the increase or decrease, if you understand on a larger scale, all of these fields are acting the same way, then you understand that X factor determines the Y factor of weather.
Okay, so this is a pretty good answer. This is more except for some stuff which I cheated and didn't tell you, but this is more or less the right answer. So I will.
It's not a statistical question.
It's a question about technique. So it's a statistical. The statistics can go either way, but the question is, how can I quantify it? If I have this table, what will I do in order to answer this question?
Statistical table that can tell you what the connection between each variable to other.
Yeah, so I agree, but I can visualize it and show you this visually, which is what we have here. Okay, quite abstract. I like the colors. So what we see here on the x-axis, we have years. This is from 2010 until 2017. We have here 80 blocks of Chardonnay from Napa and Sonoma Valley. That is no surprise. And I normalize the yield, so because different blocks have different densities of trees, and they may be treated in different ways and be targeted towards different programs of wine production. I will not throw the details on you. So I'm just asking for every block how well it performed in every year compared with its average. So if a block has, let's say, a y-axis of 1, is my pointer there somewhere? No. But anyway, on the y-axis, if you see a value of 1, then that specific field performed on an average level. If it's above 1, let's say 1.5, it yielded for a given year 1.5 of its average yield, etc. Okay? And there is a very clear trend here. We see that most fields follow similar lines. They follow similar trends. We see that in 2011 and 2015 and 2017, yields were relatively low. We see that in 2013, yields were relatively high, and the other years go somewhere in between. And now we can ask ourselves, okay, so what is the standard deviation of all of the yields, which comes out as 30%, and what is the average standard deviation if I look at every year by itself? And here the number turns out to be about 20%. Okay, so out of the 30% of year-to-year variability of fields, a third is explained, or at least a third is explained by regional factors, and around 2/3 are explained by field-specific data. There are some caveats here, because, for example, if I have a field that faces north and a field that faces south, and I have a warm year, they may be affected differently. So I really want to say is that the third explained by regional factors is only a lower bound. It can be higher due to the reaction of specific fields to common conditions. Okay, for example, again, soil types, other kind of stuff. Okay, and because this is already good enough to work with, and because weather data is relatively easy to come by, and this is probably the immediate suspect that is most affecting yields year over year, so we went and grabbed some weather data, and then we saw this. So weather data is a mess. Why is it a mess? So what we see here, we see on the x-axis we have the day of the year. So 0 is January 1st, 2013 in this case. This was the best year, to remind you. on the right-hand side, 350, etc. That's the end of the year, end of December. To make sure we're all on the same ground, grapes are being harvested, or they set fruit once a year, and that fruit is being harvested sometime around day 300. Okay, so this is a relatively good representation of the weather that a given a vine is experiencing. This is for Sonoma Valley, and on the y-axis we have the temperature, and we get the temperature at a very good resolution, 1 hour resolution, which means that in every year we have about 7,200 readouts of temperature. And we can see the clearest trend is that winters are cold, summers are warm, the middle is higher, the ends are lower. And the other trend that we see is that you have large variability in every day. And the daily variability in weather is so high that in fact the high temperatures in the winter are higher than the low temperatures in summertime, etc., or vice versa. Which means that this is a very complicated signal to analyze because I cannot just smooth it out. If I smooth it out, I will lose all the peaks, heat waves, cold waves, frost, etc., into the global trend of saying, okay, winters are cold, summers are high. It's very hard to extract from weather data the exact features that will affect or that will create a difference year to year. To give you another example of weather, this is 2011. This was the worst year out of the data set that I showed you. Also, winters are cold, summers are hot. It looks somewhat different, but it's different in thousands of ways. If I overlay the two, one on top of the other, to look at the diff between them, I can see, so here we have 2011 in blue, 2013 in orange, and every place where I see orange and not blue, it means the temperatures, this event occurred in 2013 but not 2011. Wherever I see blue and not orange, it means that this event occurred in 2011, not 2013. For example, we see that in the beginning of the year, we see that there is this area here. So nightly temperatures were lower in 2013 as opposed to 2011. Maybe this is the drive for the difference in yield. I don't know. We look a month afterwards. We see this. So temperatures in February were statistically or significantly higher in 2013 compared with 2011. Maybe this is the factor, and we have a bunch of these throughout the year. And the problem is that all of them can, it's very hard for us to dissect which ones really had the effect. And generally speaking about the complexity in weather signals, so we have a very small set of labeled data. Why is that? Because the weather only happens once a year. And we have this kind of data maybe for 20 years, something like that. And so we have 20 such years of hourly weather data. You may argue, okay, but you can take weather from different geographies. But once you do that, there are other factors at play. Because, for example, if you move north or south, the amount of daylight time changes. And that is something that is consistent in a specific geography. And if you move south or west, then there are many other characteristics, soil types, etc., that also start to vary. The different, yes. Yeah, if I consider if I ask myself, the entire annual weather affects the yield. So I have annual weather. I can only get that. Like a row for me is the annual weather, and at the end I have the label data. That's the average yield of the region. How many rows do I have? 20 for a given region. And for different regions, other factors can be at play. So I have 20 rows, and each row has 7,200 columns. And I've been gentle on you because we also have precipitation, wind direction, radiation, etc. So it gets even worse. And now go and deal with that. So that's one of the challenges. I talked about promise and challenges. So letting you see some challenges. And with that, let's move to another kind of data source. And now let's go into field level data. There are many kinds of field level data which we can analyze. Here I'll look at satellite imagery. And what we see here is we see satellite imagery. We move to Israel now. This is in Otef Aza, near the Gaza Strip. This is the field of potatoes. And we have here imagery from starting January 1st, 2019 until about mid-April. And what we see here, this is not the visual spectrum. We see here something called NDVI, which is a vegetation index. It's a standard formula that For every pixel tells us how strong a vegetation there is in that pixel. The resolution here is about 1 meter per pixel. The greener it is, the more vegetation there is. Okay? And what we can see, so we can see that the field, and we have here pictures approximately every 2 to 3 days. Okay? If there are clouds or maybe missing pictures or other issues, but generally it's every 2 to 3 days, which is amazing. Yes, in terms of temporal resolution, it's really amazing that we can get this kind of data today. And what we see, so we see it starts kind of yellowish, it moves on to being more green. At some point it turns, there are some fluctuations there. Let's see if I can get my pointer to appear. For some reason, did it move? Yes, thank you. Okay, and then at some point there are some fluctuations. Here it's a little bit more yellowish, greenish again, yellowish again, but at some point it declines and becomes practically orange and red, which is probably when the field was harvested. Now, you don't need very complicated image analysis or vision in order to analyze this. The simplest thing to do would just be take the average. Let's ask what's the average vegetation on this field. And if we do that, we did that for a couple of dozens of fields. I hope you can see the dots. So here, every subplot represents a real block in around the Gaza Strip of potatoes. It starts at the beginning of January 2019, and each point represents the average NDVI for that field. And you can see a clear declining trend, which means that we can use this data in order, for example, to predict when the growth cycle will end. Again, to make sure we're on a common ground, so potatoes are annuals, which means that the plant starts, it grows, it creates leaves, and then when it ends its life cycle, in this case, you can see most of them ended their life cycle around March or so, then all the leaves drop dead, the potatoes remain in the ground, and they can be harvested or collected and used for production. So we can see here that we can use this kind of data in order to give you field level maturation predictions. And there are also other things we can do. We can also extrapolate from here yield and other factors by taking into account the height of the NDVI and for how long the field has been in this NDVI. We can of course use that again with weather radiation to get some estimates about how much radiation the field absorbed, which also contributes to yield and dry matter. You can also appreciate that the data is quite noisy and it's not very consistent between different fields. So to sum up about satellite imagery, and as I said, there are other signals as well, there are a few issues here. Spatial resolution, I see a drone here, which means that we'll talk about spatial resolution later. But a high resolution satellite imagery will have a 1 square meter resolution. This is very gross. And if you look at satellites with a higher radiology capabilities, you'll often drop down to 10 meters or 30 meters per pixel. It means that if you have a tree that is sick or something like that, no satellite imagery will be able to assist you there. Temporal resolution is also an issue. This is very high temporal resolution, but if we go back, let's say 5 years, or depending on the area you want to get covered, you may get a satellite image every 2 weeks or even a month if you happen to have clouds. And of course, if you are in a cloudy area, again, it really hampers your ability to get updated imagery for that area. Signals are often not consistent. Pictures are taken at different times of day, in different angles. You may have clouds shading the field, so even though the field is exposed, it does not see the same kind of sun and therefore reflects differently. The field may have been irrigated or not irrigated by spraying, which will also affect the reflectance, so it's a very noisy signal to work with. Lack of historical availability, at most 5 years, so if you really want to get a data set and ask yourself, okay, could it be that I'm picking up the wrong signals because of regional factors, etc.? It's very hard to dissect. And also cross-referencing labeled data. So you need to know exactly where the fields are, what was planted there, if they have been subdivided to different varietals, etc. You need to get all this data in order to be able to say something about this field. So again, it's a promising signal, but it's also quite complicated to deal with. And the last kind of application or direction I want to show you has to do with production lines. So a completely different kind of data. And this is a potato chip factory. And here we have on the x-axis the weeks. This is for 2018. And for every week, we see what parts of the product, how much waste was accumulated or generated in each part of the production line. Okay. So, and this is a breakdown, and the y-axis is how by percentage. Okay, so you can see here how much percent of tonnage or of the crop of the processed material was wasted at every part. And first of all, I want to get rid of the orange line that dominates this. This has to do with mud and leftovers of sand, etc. So this is not really waste. It's just a matter of we weighted X tons, but 5% of that was due to the potatoes being grown in a muddy ground or being wet, whatever. So let's clear that off the table. But something interesting we can see is with the green line over here. And the green line is for sorting out small potatoes. And we see that the year started by having about 1% being lost for small potatoes. It then jumped to about 3%, 2 to 3% for most of the year. And then around week 35, it dropped again to 0.5%. And we went to the factory owners, asked them, okay, so what is going on here? And they said, we installed, when the potatoes are before they're being processed, they go over a net. And this net has holes in some size, and the small potatoes fall through the net. And they changed the net to have a net with larger holes. And once the net had larger holes, more potatoes dropped in the holes. Now, of course, they had their reasons, but they didn't even have good measurement to track this and understand how much potatoes they were losing. And we're talking about 1 to 2% of potatoes that were lost. And at the end of the day, they figured that out eventually after like half a year, and then installed back the net with smaller holes. And all of a sudden, you get 2 more percent of potatoes being able to be processed. So this is one example of interesting stuff going out in the production line. And another one is the blue line. The blue line has to do with cutting and sorting. So once the potatoes, after they pass the net, they go over a kind of a ramp where people are sitting and looking at the potatoes. Some of them are already sliced in half, or they will slice them in half in order to look, and they will throw away every potato that is rotten or green or is misshaped in a way that will cause it not to be able to be used to generate nice looking round potato chips. And what we can see here with the blue line is we see that at the beginning of the year, in the winter time mostly, so in this area as well as in this area, there was large loss or waste in this station, in this place in the production line, whereas throughout most of the year this was relatively low. Okay, again, large jumps between 1.5% to 4%. Really lots of potatoes went lost there. And this has to do with timing. So throughout, when the waste year was low, it was because the potatoes were brought either directly from the field, so they were fresh potatoes, or from relatively short amount of storage in refrigeration, which is how potatoes are stored, because the factory has limited capacity. And when the losses were high, it was due to either imported potatoes that had to go through at least the Mediterranean, or potatoes that have been stored longer in refrigeration. So again, there is the opportunity here to play around with production line capacity versus refrigeration and importing of potatoes. Perhaps there are other things one can do. For example, you can change the seasoning. If you're using darker seasoning, you may be able to process potatoes even if they're slightly darker. If you're doing only light colored seasoning, like just salty potato chips, you must have the potatoes be bright enough, let's say. So you can play around with that in order to reduce your waste. There are many challenges in working with manufacturing data, especially when you try to correlate that with field level data. This is siloed data. It sits in different systems, specialized systems, need special access rights. It's indexed in a completely different way than field level data. This data is indexed by shifts in the production line. So it's very hard to understand, to correlate or to assemble a data set that can say, okay, this is the weather, these are the potatoes, this is what happened in the field, and this is what happened in the production line. Very challenging data engineering wise. Oftentimes this data is manually entered, which means it suffers from all kinds of errors and mistakes, and it's very manufacturer and production line specific. So in terms of scaling up, it's quite challenging. But again, these are the challenges, but there's also a promise. And with that, I'd like to conclude. So big promise, many challenges. If you're in, we're hiring. My email is at the bottom, and yeah, that's it. And I'll be happy to take some questions. We're nearly at the end of time, so we have like a minute for questions if anyone has any. Thank you. So we are working in all of these directions, and we're most matured in terms of yield predictions for grapes for wine, also yield predictions for potatoes. These are our strong points now. And we're looking to expand into more verticals, more geographies, more kinds of crops, as well as refine our predictions and algorithms to give you better predictions, essentially. But really, there's like tons of work to do. So wherever you look, there's something you can do, and the hard problem is to decide what it is you want to focus on next. Yeah. Yes.
Satellite? Sure. Are you using free satellite data?
So for the daily data, you cannot get that from free satellites. For that, we pay. We pay Planet. Planet is the largest company, has the largest coverage of satellites today. And there are free satellites. They will give you every 2 weeks or a month worth of resolution. They have very good radiology. So in terms of consistency of signal, they are pretty good. Yes. So we give to customers, we're a software as a service. Okay.
All right, so I'll repeat it and enhance it.
I also forget about the people in the top.
Is the final product of the company the predictions themselves? And the second question is, are you going to offer this as a service, as a product? Is it project-based? Because it sounds very customized, very tailored to each specific case.
So good question. So this is not a product forum, so I didn't go at all into what it is. I only spoke about what our data science team does, not about what the product of the company is. So the product of the company is essentially, we're a software as a service company. If you are a food company, we provide you a solution that enables you to track all your fields in real time. You can enter real-time data from the fields if you conduct field measurements and stuff like that. It's all being ingested and processed in our platform. It presents to you our predictions, and we're now working on optimizing also all the logistics and operational concepts of the production line. But we provide an end-to-end solution for food companies that are operating in what we call an integrated supply chain system, which means that they own or at least have agronomies and teams that actually scout the fields and track them. Yes. Anything else? Any other questions from the top, maybe? Yes. No, so we are not a hardware company. We're not using, if our customers already have some kind of IoT, smart precision ag solution in place, we'll obviously like to have this data, but we are not deploying or using any sensors of our own. So we're only using what is available. So if our customers, for example, take bricks measurements, sugar measurements of their grapes in a vineyard, we'll get these measurements, we'll use them in our predictions. But we are not supplying them with solutions in order to track this, except for data entry solutions so that it can be tracked and also used in our system. Okay, good. So thank you so much.